Hello, everybody. Today I'm going to talk about software as a service architectures. How many here work on something that's a service and generally available through the cloud or like an on-premise installation, like not an app or something? So that's a fair number of people in the crowd. I stumbled into software as a service largely through my open source work. I built Python software for a really long time, particularly in the web environment. And the most obvious thing you do with that, if you want to make money, is build a service. And this is sort of experience from the company where I'm currently working, as well as consulting I did before, and companies I worked before, just how to build the first parts to building a software as a service business on a technology stack level. I blog a lot. You can read some of my stuff there if you want like more in-depth coverage of some of the things I will talk about, or you can follow me on GitHub and Twitter. So this is I guess the thing that I'm most known for is a Python web framework called Flask. I built this about like 8 years ago at this point, and I think it's one of the most popular ways to build Python web applications at this point. But currently, I'm working for a company called Sentry, and we are doing crash reporting. And it's also an open source project similar to Flask is one, but unlike Flask, which is a library or a framework, Sentry is an application that you can either install yourself or you can use the cloud version, which we distribute to customers the same way as we host it ourselves. So I like software as a service, and the reason for this is that I like open source. And open source often has this problem that you don't quite know how to make money with it. But with a software as a service business, it's a lot easier because you can still keep the entirety of your stack, or at least the vast majority of your stack, generally freely available for people, because people actually do not want to run it themselves if they can just pay someone to run it for you. So Sentry is 100% open source, other than the billing and some other stuff. But the vast majority of our customers are paying for the software as a service version. So what is software as a service? I think the most important part is it's multi-tenant, which means that you have one installation and many different individual tenants can operate within that one installation. A tenant in this case can be an individual user, or in case of Sentry, it's an organization. So you can join Sentry, which is our service, as an organization, and each organization has multiple teams and users, and the organization as such is considered a tenant. The alternative to this is sort of the single tenant self-hosted version you can install, or you can manage for others. So if regulatory requirements force us to put users on an isolated individual installation, we could theoretically, or also in practice, but we don't do it that often, take the entirety of what we have, put it on a AWS cloud, which we manage for the customer, and then they're in control of their own network. And then the third one is you can just ship off what you already have and give it to customers, and they run it themselves. And you can do this almost with the same code base. So the way we structure it is the majority of the code is shared, and we just ship it off and then see what users do with it. All right, so the patterns that I'm going to show here are largely universal and don't really apply to programming languages. There are 2 slides where there is some code on it, which will use Python, but the concept is the same. All right, so the building blocks of software as a service, as far as I'm concerned, is make it as boring as possible. One thing that I learned is that you can very easily get hung up on the idea that it has to be ridiculously scalable. You have to start with a microservice architecture and lots of individual bits and pieces, use fancy new technology you learned about, or you go to a talk and you hear someone else build something similar to you and you try to copy the architecture. And you can easily get hold up with just building architecture and not so much building the product. You can get very, very far with a very basic setup. You could, for instance, pick a SQL database, like a very basic caching system. You can use Redis for this if you want. And then maybe if you have some things that need to be decoupled from the request response system, you can use AMQP. Or to make it more concrete, you can use something like RabbitMQ. And I think this is all you need as a start to actually build something reasonable. And the nice thing is that it's entirely open source. So you can start with something straightforward. Sentry to this day is still running on Postgres. It's still running on Redis. It has some memcaches as a legacy layer. It still uses AMQP for queue communication. we have very little fancy technology. I think the fanciest we have is we use React for storing large assets, and that's pretty much it. And we are doing reasonably well on this infrastructure. We will eventually have to go to something that's more specific and like evolve it into areas where we have multiple services, but you can get really, really far with a very basic infrastructure. So the foundation for most software as a service is security. And this is something that different companies have different approaches to. Sentry, if you look at the history of that particular product, is an open source project which started as a single tenant application. You just ran it on your infrastructure and there was stuff on it. So a lot of the access control had to be retrofitted into the software. So that's the part where I would say that if you started from scratch, you can do much better than we are doing. So if you only take one thing away from this is security and context is very, very relevant and matters. When I talk about context, I mean it should be possible at any point in time for an application to figure out in which state it is. So you can imagine this. You have an HTTP request that comes in, and a random function is being invoked from that HTTP request. You want that function to be able to figure out at all times what its state is. So it wants to have a security context. It wants to have the idea of what the if that function needs to validate in some form or shape what its current tenant is, if the current authenticated security user is having access to a resource or not, it should be always possible to do that. Even if you want to do it explicitly, to say like I want to operate on this organization, it's dangerous if the system doesn't prevent you from doing things that you don't want to do. So the concept I want to introduce to you is what I call tenant isolation. It's the idea that you have, for instance, thread local data, which is a variable sitting somewhere which you can always contact to figure out what the state of the current thread is. And then you can store information on that variable to, for instance, identify the current request, identify the current tenant. And if at any point in time that variable doesn't have a value yet, you can run some logic to put in a reasonable default. So for instance, if we are asking for the current tenant, we could say, like, is there a current tenant? If we don't have a tenant yet, do we have a current request? Can we derive what the tenant is based on the data in the request? So for instance, we can go to the authorization header in the current request, try to figure this out. But if we are operating, for instance, in a cron shop, which doesn't run in an HTTP environment, then something else has to put the tenant in place first. So that's sort of the idea behind this, is that you don't have to pass data through the system. You could do it. You could pass a context object down. Like, for instance, if you use Go as a programming language, you might not want to use thread local variables, but you could pass down a context object. But the idea is the same. You have one bit of context information that you can always contact to figure out how am I doing. So the reason why this is really, really important is because, like, the vast majority of security problems that I have encountered in software as a service applications, other than I don't know, cross-site scripting and boring things like this, is people not scoping the operations to the current tenant. So for instance, someone might write a function which batch updates, in this case we have projects, and you want to change the projects to have a different state, and you take just project IDs. If someone were to be able to pass arbitrary project IDs into it, which are not the project IDs of the user that is supposed to operate on it, you might just override it. So in this case, whoever wrote this code didn't look at, like, do I have to scope it down to the tenant? What happens if you pass some stuff in? So with the idea with automatic tenant scoping is that the base layer of your database query system can at all times contact the current tenant to see I can automatically scope down my projects to the current tenant. So in this case, whenever I query the project, the query will already be restricted to the current tenant. So you cannot screw up. I think that's probably the most important part if you run a multi-tenant application, is to make it as easy as possible for developers to not screw up. Because if anyone at any point finds a way to access data from other customers, that is a really hard problem to solve. Because especially if you don't have audit logs, you don't quite know what happened, and if someone actually had access to data that they shouldn't have. The same idea of having thread local data to get access to the current tenant can also be used to scope the permission concept within the current user. So for instance, if you have an organization where the user can be a regular user or it can be an administrator, you want to be able to say, like, what is the permission that the user has? And then separately, you want to be able for a user to use a subset of permissions that are available to the user for the current context. So a good example is if you authenticate, say you use authenticate with Facebook, the application that wants to operate on your Facebook's account can tell Facebook what the intended scopes are. So it can say, I only want to have access to your email address. So any API calls that the application would then do on your user account that would give, through the API, access to more data would be denied. So one way you can implement this is you have the idea that there's a current user, which is not the tenant, but the user operating within the tenant. And then you can say, like, if there is no user available, then we will just say that the only scope you have is anonymous access. At any other point, we take all the scopes that you have as a user. So for instance, it could be administrator scope, access to email scope, whatever scopes you have for permissions. And then you can restrict the scopes specific to the current request. So for instance, if the current request is authorized through like OAuth application, and the application has like, I only give you access to, for instance, anonymous data and email address, then in the scopes from request authorization, it would only be anonymous and email address, and then the result of the current scopes is only the email address. And then at any point in time, code can always refer back to the scope list to figure out how it's working. So you have one central place which anyone can call and figure out what the current security context is. This is making life much easier, and it makes auditing much easier for you as a developer to just look at this one piece of code which is used all over the place to figure out how access logs works. Auditing is also, I think, a much more important part, because you might be in a situation where you operate a software as a service business and you have a lot of customers, and a customer encounters something, for instance, data was deleted, and then you need to figure out why was the data deleted. So being able to go to an audit log to figure out what dangerous operations were executed on the customer's tenant are important. So one way you can do this is to have the concept of a general audit log. It's a function, in this case called log, which you can call at any time with like an action, for instance, like project deleted. And then you can add some additional message, metadata, whatever you want. But in addition, the log function will take whatever contextual information is available and attach it to the log record. So for instance, if the request which modifies, for instance, which deletes a project, as an example, comes through an API, and the API is not authenticated as a user, but is authenticated for like a system access, then the user might not be available, but we can say which IP performed this operation. If we have a user, we can add the user directly to the user context. So the idea is that someone who potentially writes any dangerous API can just call one function, and the function in itself will figure out as much information as possible and then store it in an audit log. And then you can get later in and figure out like which users modified something, which tenants were modified, and so forth. And making this as trivially as easy as possible saves you a lot of headache afterwards, because not having this information can be really annoying. You can try to get to web server access logs, but that's like an enormous amount of like useless information you really don't care about. And they might not even carry enough data to be able to tell what actually happened on the system. And this all is supported by the idea of having a context available at all times. Likewise, you can take this general context information further to automatically provide translations specific to the user's language and stuff like this. So you can take this concept as far as you want. So the idea that there's a context which has useful information available at all times is quite useful. For, I think, most people, the idea of starting out with software-oriented architecture sounds appealing because everybody's doing it. But I would strongly encourage you not to start there, because service-oriented architecture is ridiculously complex. You need, the moment you have two things that need to talk to each other, one of them might stop talking, and you need to immediately decide what's going to happen when they stop talking. And the more of these little bits and pieces you add, the more complicated it gets. I think Sentry at this point is like, I don't know, 70 servers or something, but they are all split into maybe 3 groups. It's like workers, it's request handlers, and then there's some general batch processing going on. But they don't have a lot of individual behavior. So for instance, we don't have workers that only send push notifications. So we don't have workers that only do I don't know, very, very specific services. So we are going to eventually end up in an environment where we have individual services which only have one task and they talk to each other. But that requires a lot more engineering. And for many people, they will never reach the point where this form of engineering is actually necessary. You can build a monolith and make the monolith internally well isolated that you can, if you want to do it later, split it off individual services. There's no reason to start there. So you can start simple and then evolve it from there onwards, and then also design the architecture of the system as you go. It might turn out that the database that you initially thought is the best database to pick doesn't have support a couple of years downwards, and you might have to redecide anyways. So the idea that you have the data in a very good format, like for instance, a SQL database has a good advantage that you can from there go to any data store which takes some liberties to achieve scalability that takes away some of the data access that you would have. So with a SQL database, you're quite reasonable long in the situation where you can get access to all the data in your database, and you're going to get a reasonable answer. The moment you relax some of the constraints on this, that moment you end up with messy data. So I worked in a company before where we had lots of data in a MongoDB database, and we couldn't actually access it in the way which required to answer some simple questions about the health of the system, because just the way the data was structured didn't make this possible anymore. So starting with like a simple database and then evolving it from there saves you a lot of headaches. And especially initially in a business, you kind of want to be agile and actually be able to shift around a little bit. SQL is great. So instead, we focus less on scalability and more on developer happiness. So custom linters on commit, I think, are good. Everybody should do that because it means that you catch a lot of problems before they actually go into version control. So we do this on the main Sentry code base and a bunch of other things as well, where you just commit, and if the commit doesn't pass linting, it will prevent you from committing this. There are obviously ways to override it if you really have to. But it's an easier way to catch things that shouldn't happen, especially if your test runs take too long and the test runs also run through linting, then that might catch a lot of stuff that would otherwise take down some of the ability you have to respond to these problems. Then we keep the master branch stable at all times, so you can always check out the master branch and it will work. And we do feature developments and merge the features in very quickly, and I will cover this a little bit. We have strong understanding among our developers that data and code have to be bidirectionally compatible. We have so many services that we can never guarantee or so many servers that we can never guarantee that all the servers run the same version of the code base at all times. Likewise, the data might have already partially migrated or not. And we need to be able to support rollbacks, and we don't want to ever have downtime. So the way we do this is data migrations are written in a way where old code and new code can work with the same data and not screw up the entire thing. And this is something that people have to understand when they do code changes, that this is important. We want to be able to not go down and go up and down data migration-wise. So if someone causes downtime by not following this would not be great. But because this is part of what we teach people, that doesn't really happen. So fast iteration for us definitely trumps scalability. In particular, for us, it's great because we have a queuing system in front. So if someone does push some code which has bad performance characteristics, we never lose data. We can just go back and then run with the old code, catch up on the queue, and try to figure out what happened. So we focus on quick release cycles. And one of the ways in which we can do this is people's local development environment is reasonably close to production. So people don't have to push stuff to production to figure out if it will break or not. So we put a lot of emphasis on keeping it as simple as possible. And you can more or less expect behavior on production on your local development environment. Also, it takes, I think, less than 10 minutes to actually have a development set up on your local computer, which I think also helps in hires that come new to the company to feel less overwhelmed by what they have to learn. So I think there's something that we have a lot of focus on is like make it as easy as possible for users that are new to the development experience to actually have a good time in this. For us, that became sort of natural because we're an open source project. So we always had an emphasis on we want to have more external contributors being able to work usefully on the project. It's obviously much harder if you already have started with a little team of people that are sort of close to the outside. But it's definitely something I would recommend others to follow, the idea that you can easily start out with development. So I don't know how much we still follow this, but we had the idea that every new hire should be able to push a new feature into production on the first day they work. And so we have a lot of emphasis on making it hard for users to screw up. When the users in this case means developers, make it hard for developers in the company to screw up. And then we do all the feature development on reasonably short pull requests. The tricky part there is that a lot of features that you develop are significantly larger than can fit into a single pull request. And we ship master to production every couple of hours. Whenever someone feels like they want to push out to deploy, whatever is currently on master goes out, which means that larger feature development is a little bit trickier. And the way we do this is we develop features basically on master, almost on master. So people push into feature branches, they develop some stuff there, and then hopefully in less than a week it merges into master. But if the feature is not ready for public consumption, we hide it from the user experience. So it will either just be that the UI doesn't render, or it will be disabled by some feature flag. And when sometimes we have some features that we feel more confident that users want to use them, we have the concept called an early adopter. So if you opt into being an early adopter, some of the features that are hidden for the general population will be showing up for you. So it can totally happen that since we ship a new release to on-premise customers every 6 weeks, that there will be features going into on-premise installations that will never go live, and then when they update in 2 months, the feature that they already had but never saw will be removed again. So we had a bunch of situations where there were data migrations for features that no one ever saw other than us, but it was still in the main code base. As I mentioned before, the way that we handle this is through feature flags. And one of the sort of, I think, better ways to deal with feature flags is so in our case, they're reasonably straightforward. We have a set of features like, can I see this particular feature? Can I use this particular UI? And we opt in and opt out users based on flags that are always available. So for instance, the development team at all times sees the features that we opt in for ourselves. So you usually see, since we use the product ourselves, we can see more than the average customer sees. The downside of this is that when you always run with your own user experience having all the flags on, is that it has happened before and it will happen again, that we break something for users that we don't see ourselves because we always have the flags on. So like there will always be some small things that you might not catch in unit tests. Some of the ways in which we try to combat this is we are now screenshotting the vast majority of our code base. So we take views which we expect to have a certain shape. So for instance, we have a view where you can see all the issues in your project. And we will screenshot them. And then we use a service called Percy to run visual diffs on them. And then if we see if we merge a pull request, the visual diffs have to be either matching or someone has to approve the changes. So that helps combat this a little bit, where you might only see the version with a feature flag on. But generally, I gave similar talks to this one before, and the part with the feature flags, I think, always had the most discussion, because many people feel like you create a messy code base by pushing a whole bunch of stuff into master, which might not even belong there. It's significantly less of a hassle in reality than you would expect. We are very eager in killing old features. When a feature is permanently on, we will eventually remove all the switches from it. So it's not nearly as controversial as this seems to come up all the time. So you can definitely merge stuff in early and often. And with that, I am happy to take some questions to the general topic or anything that comes up. I don't know if do we have to use the app or?
we have the mic, so it's totally fine. So any questions? Anyone? Right.
So I have a question. You take also the features out of your code base of the master. So because you told that you push in the new features as soon as they are ready, but probably not visible to the end customers. So you have also the part in I don't know.
There's a part in development cycle which will clean out features. Yeah.
Okay.
And it's up to the individual developer's responsibility to eventually kill these things.
Okay. Okay. Thank you.
All right. Anyone else? See hands? See hands? No hands? All right. All right. No, nice. There you go.
How are you setting up the local development environment that it emulates the production environment? Are you using Docker or?
So we are not using Docker. That will eventually change, but I have a very strong opinion and I don't want anyone to force using either virtual machines or Docker. So our base software package is Python. So that's what the infrastructure is built in. And we have, we just use standard what's called virtual envs in Python to manage this. We do have some scripts for users to get the initial setup going locally. But it has some really nice advantages having a very lean stack because it doesn't, like, Docker gets pretty close and we were running some experiments with it, but at least a couple of months ago there were still some issues with file watchers between the inner and outer environment if you were running on a Mac. And we do like auto reload and all of those nice features, and we don't want to force people to actually have to change stuff within the Docker image. So that's the basic answer. So people only need locally to run Postgres. We have a very lean stack, so they only have to run Postgres, Redis, and some Python processes, and that's all they need. And we have abstraction layers in between to for instance, we have what's called the blob storage. The blob storage is what in production runs on React. For local development, the blob storage runs in, I think, a Postgres database. So there's some of the systems are shimped out so that you can switch to a different implementation of it. And then only if you change that implementation, it gets tricky. And this also helps us with getting the software running on people's machines that don't have the mental capacity and manpower to run like a cluster of React machines, so they can use the different backend.
Okay, but if you update the Postgres database or something, it has to be the same version locally and.
So for us, again, it's a little bit different because we are an open source project. We have an on-premise version that we don't require a specific database version in. So we actually support Postgres down to 9.1. And we don't use any fancy features up. It gets a little bit weird because we also technically still support MySQL because we have some legacy customers which are on MySQL. So we can't get too fancy with some of those features. We do, however, have some code paths which were like, if you're running a reasonable version of Postgres, we can do something cleverer. But so that makes it also easy for people to get started quickly. They don't have to track a specific version.